Let's start. So today we discuss something called a matrix factorization. So factorization means, it is called in Korean. Does anyone know what it is called? What is a factor or factorization? In Korean, it is this 인수분해. Okay. So what we are doing in the matrix factorization or doing 인수분해 on matrix is, so if you know the typical factorization, you guys know this is factorized as a product of multiple factors. Okay, so this is a factorization. So in the case of matrix factorization, so we are given the original matrix A, and then we want to factorize this matrix as a product of multiple matrix. So maybe we can represent matrix A or rewrite matrix A as a product of the multiple matrices. Okay, so there are at least maybe 100 different matrix factorization. And today, as a starting point, we will start to learn the very first matrix factorization in our life. So that is called a LU factorization. Okay, and so why it is called LU factorization is because we represent or we factorize matrix A as some matrix called L and some matrix called U, and then this guy is representing lower. So it's L is an acronym for lower, and this guy is an upper. Okay, and then lower triangular, and then upper triangular. So so we are given a particular matrix, and then we represent it as the product of these two matrices, and then this is an L and this is an U, and then by lower triangular matrix I mean that only the non-zero entries are the lower triangular part of your matrix, and then also this upper triangular means you will see the non-zero entries only on the upper right part. Okay. So you want to decompose some matrix A into a product of these two matrices, okay, one of which is a lower triangular and then the other is an upper triangular matrix. And then this upper triangular matrix is actually what you already know very well, which is a echelon form. So if you think about the where the non-zero entries are placed in your echelon form matrix, then it is all the non-zero entries are upper right part. Okay, the lower left part are all zeros, right? So that way, this guy is nothing but your echelon form matrix. Okay. So it's just ending up with just row reduction. Okay, so you just do the row reduction on the matrix A, and then you will change it into the matrix U, which is your echelon form. And then, so if you recall or remember what we learned in the last time, then we kind of observed or obtained a similar form of this. So in the case of row reduction or row operation, we multiply maybe e to the e of k, okay, In that case, you will obtain some echelon form matrix U. Okay. Okay, so from this form, each of E1, E2, and EK are each individual row reduction, and then all together as a product. And let me ask the question: is this part invariable or not? Yeah. So if we remember what we learned last time, if we start the matrix A as a square matrix, for example, 3 by 3 matrix or 4 by 4 and so on, and then if we can end up with reduced echelon form as identity matrix, and then that's when this matrix A is invariable, right? Then now, instead of reaching or instead of converting it to reduced echelon form, we just arrive at echelon form, not all the way to the reduced echelon form. Okay, and then this part, if this guy has an inverse, okay, so if this guy has an inverse, and then this L part can be viewed as the inverse of this part, right? So if we call this guy as maybe B, okay, and then if B has an inverse, and then by multiplying B inverse on the left, okay, and then we will obtain A here, and then B inverse will be will become our lower triangular matrix L. Okay, so so here we have a few questions that we have to answer or we have to think about. So the question is this part B, the product of elementary matrix or the matrix corresponding to the row reduction, are these matrices invariable? Okay, and then also the second question is, so given the form of this LU factorization, if we obtained echelon form, and then it will just it will be upper triangular matrix, right? It will be always satisfied, but at the same time, another thing that we have to think about is, even if this part is invariable, then is the inverse of this part is lower triangular. Okay, so the first question is, all these elementary matrices or row reduction and their corresponding matrices are invariable or not? And then the second question is, if it is invariable, is the inverse this lower triangular or not? Okay, but if we can answer for those both of questions as a yes, so if the answers for both questions are yes, and then we can just change or this row reduction into this matrix factorization form, where we represent the matrix A into the product of these two matrices L and U, and then L is lower triangular and upper triangular. Okay, so this is a kind of high-level story, but although we have to answer in detail for those questions. Okay, so here, regardless of what A is, so suppose A is not even a square matrix, or A is not invariable matrix, or A is not even square, because in that case, we cannot even talk about whether it's invariable or not. So A is, for example, 3 by 4 matrix. And then let's imagine the row reduction as a matrix multiplication. So the first matrix E1 will be, what is the size? Size is 3 by 3, right? And then as you guys know, so we will use this as well in this class. Let's imagine the resulting matrix as this 3 by 4 matrix. And then yeah, it's just a review of what we learned. So these are working as, for example, 0.1, 2, minus 1. And then this guy will be associated with the first row. And then this second value will be associated with the second and the third row. And then the linear combination of these 3 rows will form the first row, right? So each row here will work as a linear combination coefficient associated with each row, right? So that's what we learned last time. Okay, so now we think about 3 different kinds of a row reduction, right? So so we have 3 possible row reduction, right? The first one is interchanging between the row, and then scaling a particular row, and row replacement is the last one. And then for each of row reduction or each of these elementary matrices, we can always think about its inverse transformation or inverse matrix. Okay. So the point that I wanted to make at this now is that each elementary matrix is invertible. So let's think about it as a transformation, which is really a row reduction, right? And then for the simplest one, which is this scaling matrix. Okay, so you guys know this is scaling the second row by 3 times. Okay, and then suppose this one is E1 times A, and then suppose this matrix became B. And then can we have some inverse matrix that actually transforms the opposite direction? So can we recover the original matrix in can we recover from matrix B into A? So how can we recover that? So if we think about some matrix multiplied here, so let's call that as maybe matrix D. Okay. Okay, and then so this is a D, and then let's think about it's the inverse transformation of this row scaling of a particular row. What would be the inverse matrix of this scaling of a particular row? So we scaled the second row 3 times, and then we want to recover the original matrix from this resulting matrix. So we are talking about some matrix as a transformation. Okay, so let me give a kind of big picture a little bit. So if matrix A is transforming a vector y into maybe some vector y. Okay, so it is so A is a transformation matrix that maps x onto y. So in this case, so if we have an inverse matrix of an A, or if A is invertible, and then A inverse and A times x will become identity times x will become just an x. Okay, So if A transformed our vector or matrices in a certain manner, and then if we can find some other matrix that can actually inverse or that can reverse that operation or that effect, so that this vector becomes the original vector. In that case, we can call this matrix as a inverse matrix of A. Okay. So in this case, we talk about some row reduction and then some matrix A. And then if this row reduction was 1, 3, 1, 0, 0, 0, 0, 0, 0. So in this case, it is scaling the second row 3 times. And then what is the inverse matrix that are multiplied here? So that the result becomes just original matrix A. Yeah, right. It's 1 and 1/3 and 1. So it's like, so we scaled the second row by 3 times, and then in order to recover the original matrix, we can just scale the second row by 1/3, right? And then that particular matrix is also itself a row reduction or elementary matrix, right? Because it's also scaling the second row by 1/3. Okay. So in this case, if you compute the two matrices, a multiplication of these two matrices, so let's call this as D, and this is a E1, and then D times E1 will become identity matrix if you compute it. Okay. So that way, if we can kind of reverse or recover the original matrix, and then that transformation matrix can be considered as an invariable matrix. What about the switching between the rows? Can you find the reverse operation? So let's think about 4x4 matrix where the first and the third row is interchanged. So they are switched between the first and the third row. And in that case, for the second and the fourth row will be the same, right? So we will have this coefficient. And then we will have ones here. So this is the interchanging row reduction or row operation, right? Do you guys understand this? So these are linear combination coefficient that will produce the first row of the resulting matrix, and then we use all 0 weights on the other columns, then the other rows, then the third row. So we picked up the third row. Okay, and then in the case of a third row, which will use this row as a linear combination. So third row will pick up the first row in the original matrix A. Okay, so this guy will become here. And then let's try to reverse this operation by just multiplying some matrix here. What would be the corresponding matrix that reverses this operation? So so it will be just the same matrix. Because if we interchange it between the first and the third row, and then the reverse operation will be just doing the exact same thing again, right? And then it will recover the original matrix. So, so this matrix, if we call this matrix as E, this is an interesting characteristic or aspect. So that this multiplication of the same matrices will become identity matrix. So the inverse of this matrix will be just itself. Okay, so that way interchanging operation is also invariable. And then the last one, the row reduction or the row replacement. Row replacement. Okay, I'll give you this elementary matrix, and then can anyone explain what this is doing? First of all, which row is not changing? Which row is not changing? The first and the third row. What about the second row? How do we make the second row in this case? What is the operation? So what is this number? So we multiply -3 onto the first row and then add it to the second row. And then that will form our second row, right? Then what about its inverse operation? So first of all, let's imagine some the row reduction matrix, okay, that we apply in next to this operation, okay. And then should we change the first and the third row? No, right? So we can safely obtain those values. So the question is this guy. Okay, what will be this number? Huh? Minus value? Can you give a number specifically? So it's like a -3 times the first row plus the second row became, so let's call this as an old, and then this is a new, right? 고기. 네. 피해를 주고 있어요. 다른 사람들한테. 학생님 이름이 뭐예요? 이름이 뭐예요? 네? 네. 박상유? 그 옆에 친구 이름이 뭐예요? 임성욱? 임형욱? 네. 박상유, 임형욱 학생 수업에도 집중하세요. 네. Okay, so in this case, we want to recover two old using the previous ones, right? So how can we make this equation? So it will be new plus what? 3 times 1, right? But here you have to think about, you have to be careful about one thing. Is this first row and another first row here, are they the same thing? So it is like, so the old first row, and here it is new first row, right? Are they the same thing? No? Why do you think so? So this is the first row of old matrix, and then this is the first row of new matrix. But as I mentioned here, we didn't change at all the first and the third row, right? So one of old and one of new, they will be the same thing, right? So okay, so it is something like this. Okay, so we now successfully obtained the inverse matrix or inverse transformation of each of these three different row reduction. So our conclusion here is that, what is our conclusion? Each row reduction or each elementary matrix is invariable. invertible, and so yeah, it has an inverse matrix. Okay, and then now let's go back to this equation. So if we imagine doing a sequence of row reductions on the left of a matrix A, and then each of these row reduction or elementary matrix will be all invertible. Each of them is invertible. And then the product will also be invertible, right? So if A has an inverse and B has an inverse, then what was the inverse of the product of them? So the first question is this guy invertible? And if it is invertible, what is the inverse matrix? In that case, B inverse, A inverse, right? So each matrix is invertible, and then the whole product of these invertible matrices will also be invertible, and then we can just reverse the order and then write the inverse of each matrix. Okay, so regardless of what A is, here each of our elementary matrices will be invertible, and altogether the product will also be invertible. And so we can safely, or we can always multiply the inverse of it so that we can represent this guy into, let me utilize here, A equals some ek to e1 of an inverse times u. So u is a echelon form, and then the left part is an inverse of each elementary matrices. Okay. Okay. So if you remember the two questions that I raised in the beginning of the lecture, are this part or is this part invertible? Okay. Now we have an answer as yes. And then the next question is this part having this lower triangular shape? Okay. Okay. And then if we think about three different row reduction or their elementary matrices, I mean, let's think about each of these elementary matrices. Among the three kinds, interchanging, scaling, row replacement, which one is not lower triangular? So this guy, which is a scaling one, is this lower triangular? It is lower triangular. It is actually a diagonal matrix, right? And row replacement, in the case of a row replacement, something like this. Is this lower triangular or not? It is, right? Although the row replacement may not be always a lower triangular, because if I give you 0 here and then 3 here, and then what is it? What is the meaning of it? So the meaning of it is we want to replace the first row, okay, and then we bring the second row and then multiply it by 3 and then add it to the first row, and then that will be our first row. So in this case, it's not lower triangular, right? Okay, so it's sometimes yes, but sometimes it's not lower triangular. But let's think about the next case, or the last case of interchange between them. Okay, so what was the example of it? Oh, this guy. Okay, so in this case, what is it lower triangular or not? Are there any cases that this guy is a lower triangular? If yes, can anyone give an example? So you always start with the identity matrix, right? So identity matrix is by default diagonal matrix, right? And then you switch between some rows. Okay, in that case, that's when we break the lower triangular structure. So it is always like, yeah, so it is always non-lower triangular. Okay, so your matrix is never lower triangular in the case of an interchange. So interchanging is the bad thing to make the lower triangular. So we just exclude, or we just simplify our word. So we just exclude among the three possible options. We just exclude interchanging option, and then we only consider the two remaining operations as our option to make our matrix into echelon form. Okay, so this LU factorization, or this part, whether this part will become lower triangular or not, okay, it is only true when your matrix A doesn't require interchanging operations. So sometimes, if you remember your homeworks or exams, sometimes you had to do interchanging, but sometimes you don't need to do any interchanging at all, right? So let's suppose our matrix A is a kind of our good friend, and so this matrix doesn't require any of the interchanging operation. So that's our starting point and starting assumption, initial assumption. Okay. And then among the remaining two operations, row replacement and also row scaling. And if you think about this, if you just try to change your matrix into echelon form, not reduced echelon form, okay? We just need to arrive at the echelon form. In that case, it is always the case that you always need no scaling operations as well. Okay, so you will see from the example. So again, I'm saying that you don't even need scaling in order to obtain echelon form. Okay, so the only option that you will use is a row replacement, and that row replacement should be also a lower triangular. So in the case of a row replacement, let's see, you don't do this kind of row replacement. You only do this kind of row replacement. So it's like this. So so we always bring the row in the upper part, and then replace the row in the bottom part. So you always bring the upper row into the lower row. In that case, you can maintain this lower triangular structure for your row replacement matrix. Okay, so this is a kind of intuition or high-level background before getting into the details about LU decomposition. So let's directly go to the example of an LU decomposition. Okay, so the overall process is as follows. So let's see. You saw this slide, and then you can easily construct this elementary matrices that you will apply. Okay, and then after obtaining this upper triangular matrix or echelon form, then you have to compute the inverse matrix of the whole thing, because that will become your lower triangular matrix L. Okay, but here if we obey our rule, that what was our rule? The first one is our matrix is so friendly enough to us so that they don't need any interchanging operation. Okay, and then we only do row replacement operation, and also row replacement is done in a way that the upper row is always brought down to the lower row. Okay? If we imagine such kind of operations, and then each of our row replacement matrices will all be lower triangular, right? Each of these matrices will be lower triangular, and then altogether the product can also, product is always lower triangular. Okay, so I'm not proving this, but we're gonna skip the proof. But intuitively, you have a multiple lower triangular matrices, and then you just multiply them together, and then the resulting matrix will always be lower triangular. Okay, and then this guy is a lower triangular, and then what's good about it as well is its inverse is also remaining as a lower triangular. So it's like this. Each row replacement is lower triangular, and then the sequence of it, or the sequence of lower triangular matrices, the multiplication of all of them is also lower triangular, and then its inverse, that will become our L, will be also lower triangular. Okay, so I'm not proving it, but so we can prove it, but it requires a little bit of a nice and elegant technique in the linear algebra. So we're going to skip it, but you can just know it, take it as it is. And then also, another really big thing, which is really good for us, is that so given this product of lower triangular matrices, computing its inverse or obtaining the inverse matrix of all these product of lower triangular matrices is really easy. So it's really easy. So you don't need to actually do additional effort or additional work to obtain its inverse matrix. Inverse matrix will just be revealed or just automatically be obtained. Okay, so this is a kind of high-level story, and so I will show you the example. Okay. So suppose you are given this matrix. So in this matrix, so there are many different, many possible different sequences of applying row replacement here. But we always follow this order. So we start from this, which is the very first pivot, right? And then we just try to make zeros on this guy, and this guy, and this guy. So like we make these values as all 0. And then this will become our pivot. I mean, it's always almost the same as what we learned as a row reduction. And then we move on to the second pivot here. And then we move to the bottom. And then make them as 0. And then we move on, and then we make them as 0. Okay? And then following this kind of order, let's think about its row reduction or elementary matrix that we have to apply. Okay, let's try to remove this guy. And first of all, we have 4 rows. So we have 4 by 4 matrix as the row reduction matrix or elementary matrix. And then let's try to remove this guy by using this. Then we have to change the second row only. And then the first and third and the fourth row will remain the same. And so 1 0 0 0 1 0 0 1 0 0 0 0 1. Okay. So let's fill this second row. Minus 2, 1 0. Yeah, you guys are good. Okay. Okay, so this one will be our first row, and then let's try to remove this guy, and then as a next step, what will be the matrix? So the first, third, and the first 1 0 0 0 0 1 0 0. And then what is the third row? Minus 1 What? Good. Yeah. 0, 0, 0, 1. Right? Okay, so you will see this value and this value. How do you obtain this? So this one is each of these values divided by this guy, but we put minus. Okay? And then, okay, so this one becomes E1, and then this one is the next step, our next step, which is E2. And then can we do both steps simultaneously or all at once by using a little bit of a composite or a little bit of a high-level row replacement? Can we do both steps by multiplying just one single matrix? Okay, so when using the first step or when using the first matrix, we actually brought the first row and then multiply it by -2 and then brought it to the second row. And then in the next step, we also bring the first row into the third row by using different multiplier. So the first row will remain the same, right? And so I wish I had more space. Okay. So how about this? I'm gonna give you the answer. One zero zero zero. Sorry about the mess. But what is the second row? It's -2 1 0 0. And then what about the third row? It's a -1 0 1 0 and 0 0 0 1. Okay, we are simply merging them into these. Okay, so in that case, it's like doing two different row replacement by using one single matrix. But still, the interpretation or how we understand it is the same. The first row will work as the linear combination coefficient to form the first row, and then the second row will work as a linear combination coefficient to create the second row, and so on, right? Okay, so so we brought minus here, and then what about this value? This value will be, oops, there should be an error here. So it should be plus, right? And then yeah, let's move on to this guy. What will be the value of it? 3, right? So as I mentioned, we remove all these guys as 0, right? And then that can be done by just multiplying this single matrix. Okay, so okay, I have to go back. Okay, so starting from A, using one single matrix or one kind of a elementary matrix that involves 3 of the row replacement. Okay, and that matrix will have. So let's see. Okay, let me use this slide. Okay, this E1, okay, will have one, 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 one here, and then there's some value. What was the value? So let me bring the value. Okay, 2 minus 1 3. Two minus 1 3. Okay, and then what about the next step? What about the next matrix? That we will have. So it is like, so given this matrix, we removed all of them as 0, and then we moved to the next column, and then we made them as 0. And then what will be the corresponding row replacement or elementary matrix? It is like 1, 1, 1, 1, and then all 0 here, because in this case, so this is our pivot, right? And then we have some value here. Suppose that is 3, and then this guy was 6 and minus 9. Okay, so you can easily form this matrix. How? What will be this value? Minus 2, right? Minus 2 and 3. Okay, so each of your matrix will have, so if you think about the shape of this matrix, so you will initially start with the identity matrix, and then the first row, I mean the lower part of the first diagonal entry will be just, you guys know that, the multiplier, right? And then the second matrix will have, okay, so this guy will have all non-zero here, non-zero here, and then the next one will also have non-zero in the next column. Okay? Okay, then so you guys remember maybe like 10 minutes ago I mentioned that the inverse of all these product of these can be really easily computed. And then I'm going to give you the answer for the inverse of the product of these two matrices. And actually I can give you the inverse of each matrix. And each matrix, so if you remember, okay, so I want to find it. I thought this one. Oh yeah, I erased it. So if the original row reduction was this guy, okay, this guy was original row reduction, and then we computed its inverse matrix or inverse transformation. So it's simply changing the sign of this value in the same place, right? So that's our inverse matrix of this guy. Okay, so if we extend this idea, we can easily obtain its inverse matrix. It's nothing but like a 3 sequential operations, and then its inverse, and then merging them together, and then the inverse matrix of it will be 1, 1, 1, 1, then minus 2. We just simply change the sign. Okay? Okay, and then you guys understand the inverse of it now. 1, 1, 1, 1, and then 2 and minus 3. Okay. Then what about the product of these two? So it's like, okay, so we have to change, switch the order, right? Because this E2, E1, we have to obtain the inverse of it. So E2, E1 of inverse will be our matrix L, right? In the LU factorization. So in this case, all together, so it's like E1 inverse times E2 inverse. So this guy times this guy. So the order should be switched. But the resulting matrix, okay, resulting matrix is nothing but just merging all these non-zero entries into just a single matrix. Okay, we just simply bring this guy here and this guy here. Okay, so we simply change the signs that we used as a multiplier, and then we just simply fill these values as by just changing the signs. Okay, and then if we had another matrix E3, and then that will fill out this value, and then the negative, changing the sign of this value, and then we bring this value into here. Okay, so suddenly we now obtain the matrix L, which is a lower triangular matrix, and also the inverse of whole process that we did here. Okay, again, our assumption was we only used row replacement. Then we bring the upper row into some bottom or the lower row. Okay, so that is our rule, because that way we can always obtain each of our row reduction or row replacement as a low triangular matrix, and altogether they become lower triangular still, and then their inverse is just nothing but changing the signs and then merging them together into a single matrix. So probably this is the entire process that we are doing on the LU factorization. Okay, so so let's just simultaneously construct the L. So if you imagine the multiplier, so it should be multiplied by 2 and then added together, right? And then what about our L? So L will start with the all ones in the diagonal. And what is the first entry? It is just a minus sign, changing the sign of this multiplier, minus 2. Okay, and then what about this guy? So the original multiplier was minus 1, and then the corresponding value for the inverse of it will become 1. Okay, and then it's like, let's see, 3, and then minus 3. Oh, is it 3? Minus 3, right? Minus 3. So, so you just simply compute the ratio between this guy and each of these values. That will form each element in our L. And then we move, and then this is our some intermediate matrix in the middle, while we changing it to echelon form. And then we move on to the second pivot. Then what is the ratio? Simply that ratio of between these three numbers, minus 3 and 4. Okay, so that will be our, that will form our L. Okay, and then the last one, this guy, so simply the ratio will become come on, minus just 2, right? Okay, so I'm trying to make it as a square matrix. Okay. It looks ugly, but this is your L. Okay. And then what is U? U is just a reduced echelon form of your matrix. Okay. And then altogether, this matrix times your echelon form, or U, that will be your answer for LU factorization. Okay. But in this case, again, if you find all zeros and 3 here, so in this case you have to do interchanging. In this case, you cannot obtain LU factorization. Although you go, you study a higher level linear algebra, and then we can handle this. Okay, but since you guys are all freshmen, so let's try to be happy. So we do not consider this. Okay, so in this case, you can safely say, okay, so there is no answer for LU factorization. So that's it. Okay, so this is the entire process, or the algorithm about how you obtain or how you compute LU factorization. And then the next question is, it's a kind of a new question. So what do we do with it? So what is it useful for? When can we utilize this thing? Okay, after factorizing it, and then if it can be utilized for something useful, and then it will be great. Okay, so let's think about why actually do this LU factorization, and then where we can utilize this LU factorization. And that is okay. So that is also for that is just nothing but making it easier to solve linear system. Okay, so once you compute the LU factorization, and then you can really easily obtain your solution for a linear system. Okay, so let me give an idea. So I'll just give the random LU factorization 2, 3, 4. So this is your L. And then U can be in the form of this. So 3, 0, see, 3, 4, 1, all zeros, and 2, minus 1, 2, minus 1, 1. Okay, so this is your LU. Okay, so this is clearly one of your echelon form. Okay, and then let's see. Then your linear system will have x1, x2, x3, x4 as so suppose you are given B vector as 0, 1, 2, 3. So I just created randomly some linear system. Okay. Okay, so if you are originally given the matrix A without doing any LU factorization, you will just do row reduction, right? And then obtain the reduced echelon form, right? Reduced echelon form, and then we'll obtain the parametric vector form as your solution. Okay, if it has a unique solution, we are good. And then if it has multiple solution, we have to use a parametric vector form. Okay, but now let's change the situation slightly. So someone gave you already this LU factorization of your matrix A. Now how can we utilize this LU factorization so that we can easily compute the solution for this linear system? Okay, I'm going to show you how. So in the beginning of the class, I mentioned L and U as lower triangular and upper triangular matrix. In this case, if your matrix is really a lower triangular matrix or upper triangular matrix, and then you can really easily compute your solution. So it is something like this. So 2x1 plus 3x2 equals 5 minus x1 plus 5x2 equals minus 1. I'm going to give you this equation, and then I'm going to give you the other linear system where 2x1 equals 3, and then minus x1 plus 3x2 equals maybe 1. Okay, in this case, in the left case, we would do just row replacement and things like that. But in the second case, between the two equations, this very first equation will only involve only one variable. So that way, it doesn't involve any other variable. So it actually makes it really easy to obtain at least that variable solution, right? What is the solution? In this case, x1 will become 3 over 2. And then we just simply plug that in here, okay? And then the solution will become maybe 2 over 5. x2 will become maybe 5 over 6. We just simply substitute the solution for the previous variable. Okay, so that way we can just plug these values into these equations that have more and more equations. And if you think about the augmented matrix or some coefficient matrix, it is actually a triangular form or lower triangular form. 2, 0, minus 1, 3. Right? So if this is your augmented matrix, you can actually start with the very first equation that only has just one single variable. Okay? So this is a kind of beauty, or how it makes it easy to compute this linear system. Okay, so we have two triangular matrices. And then, so we go through two steps here. So the first step is to make this guy as something like y. So we introduce a kind of new variable, okay, and then it will become 1, 1, 1, 2, 3, 4, then 0, 0, 0, and we have y's here, okay, so this y, and then it will become, sorry about that, we should have a three-dimensional b, so it is 0, 1, 2, okay, so y1, y2, y3, what is y1? What is y1? 0. What about y2? 1, right? And then 0 and 1, and then what about y3? y3 will become minus 2, okay? So this is called a forward substitution, okay? Okay, so our solution for y, this entire green thing, were obtained 0 and what was that? 1 minus 2, okay? So this is our y, and then now we now solve for this guy will become y, which is known as, which we obtained as 0, 1, 2, okay? So let me rewrite it. Okay. So I'm bringing this matrix 3, 2, minus 1, 1, 0, 4, 2, minus 1, 0, 0, 0, 1. Okay, so this is our U matrix. And then we have to have a four-dimensional solution. Sorry for small font. And then this should be 0, 1, minus 2. Okay. Okay, so this is x1, x2, x3, x4. What is x4? So in this case, it's like bottom to the top, right? Because the bottom equation has the only one variable. Okay, so what is the x4 here? Minus 2. Okay, and then we just simply plug that in here. And now, unfortunately, we have some free variable. Okay. And then you guys know the idea here, right? So you guys solve for the variable which has just only one variable in the equation, but in the upper triangular case, it's like going from bottom to top. Okay, so that way, we can compute this equation really easily by using these two steps. Okay, so this is this is the main usage of this LU factorization for solving the linear system. So in this case, so the beauty of using LU factorization is that, so suppose you are given A, but you are given multiple B's, okay, using the same A. So when did we see this kind of situation? It was like computing the inverse. So inverse, what was the B1? It was 1, 0, 0, 0. Then the second equation was 0, 1, 0, 0. And so we used the same A, but using different B's. So if we construct or obtained L and U matrices for the initial matrix A, and then for whatever changing B vectors, we can efficiently do this forward substitution and the backward substitution to obtain the solution for it. Okay, and then now let's do some counting. So yeah, so you are in a computer science department, so you should be familiar with the concept of a computational complexity. Has anyone heard about the computational complexity? Computational complexity. So how complex is your computation? So how much computation do you need to obtain the solution? So that is a computational complexity. And in simple cases, it is just counting the number of addition, multiplication, and subtraction and division. So we have 4 basic algebraic operations, and we just simply count how many addition, subtraction, and multiplication, and so on. Okay. So this is a simple form of thinking about the computational complexity. And so so suppose, yeah, so let's think about this example where A is replaced as yeah, A was computed as L and U. Okay, so in this case, if we have to solve this linear system, and then we have to first obtain this guy by setting up as Y. Okay, and then it will be like using this this matrix as A, and then bringing this B vector as a constant, and then we obtain this linear system, which is a low triangular form. And then in the lower triangular matrix, as we saw, so this is an inverse of the product of row replacement matrices. So the diagonal values are all ones. And so from this, let's think about the how many additions, multiplications, and so on. So in order to obtain the first variable, the solution, it will be just -9. So we don't need to do anything. But what about the second one? We have to multiply -9 times -1, okay? And then subtract it from 5 in order to obtain the second guy, okay? So 1 multiplication and 1 addition. And then what about this? Also, it is plugged into here, 1 multiplication, and then subtracted from 7, 1 addition. Another multiplication and addition. Another set of multiplication and addition. Another and another one. Okay? So for each of these values, we will have exactly 1 addition and 1 multiplication. So in total, we have 6 elements. So we have 6 multiplication and 6 addition. Okay, and then now for this guy, yeah, so time's up. So just to yeah, I'm gonna give you this as an homework. Okay, so please try to count the number of addition and multiplication and probably the division. Okay, so in this case, yeah, so let me have just maybe 30 seconds. So in this case, in the case of our U matrix, our U is not diagonal, right? So these values should be also divided by this, divided from this value. Okay, we have to have like a 4 additional division, right? Okay, so we have 4 divisions. Yeah, so you guys, yeah, I'm gonna give you just the answer. So for all these entries, we have to have 1 multiplication and addition for all these upper guys. Okay, so that's how we count the number of addition and multiplication and so on. Okay, so that's it for this LU factorization and today's lecture. Thanks, and see you this Thursday. Okay. Can you give just 1 second? 네, 여보세요? 예, 지금 바로 내려가겠습니다. 그러니까 뽑아놓고 아직 제가 시간이 없어서 못 드렸는데, 예, 저기 바로 지금 내려가겠습니다. 네. Yeah. Did I respond to your email? Can you, if you don't mind, please send me that email again? I might have missed yours.
I didn't understand one simple thing.
Okay.
And why? How did you obtain 0, 1, minus 2? How? It's in the slides.
Can you?
You explain it here. How do you obtain this one? Y1, Y2, Y3? I didn't understand.
Oh, this guy is like
0, 1, minus 2.
so if you imagine this equation, original equation, and then it will be y1 will become 0. y1 is equal to 0. What about the second one? It's like a 2y1 plus y2 equals minus 1. Sorry, plus 1. So you guys, yeah, you can plug this guy into here, and then the only remaining variable is just only 1. Okay, so that's how we kind of for the substitute.
Thank you very much.
생각이 제가 영어가 잘 기억이 안 나요. 인터체인지 하는 경우가 원래 더 어려운 경우는 저희 문제에서 저희 책에서는 간단합니다. 원래 인터체인지가 있으면 그 대각 타다 생각하지 않을 수도 있는.
네, L이 로우 트라이앵글로 안 나와요. 인터체인지가 있어요.
그러면 LU 분해하는 게 별로 의미가 없잖아요.
LU를 분해를 지금 배운 것만으로 할 수가 없고요. 그 인터체인지까지 해서 그러니까 로어 트라이앵글, 어쨌건 우리는 로어와 어퍼 트라이앵글을 만들어 갖고 리니어 시스템을 굉장히 빠르게 좀 풀 수 있도록 뭔가 준비를 해놓는 게 이게 LU거든요. 근데 이제 로어 트라이앵글러가 아니게 돼버리면 이게 조금 쓸모가 없어지는 거예요. 근데 이제 인터체인지가 끼어버리면 이제 로어 트라이앵글러가 안 되게 되고, 그래서 그때는 어떻게 인터체인지까지 같이 해갖고 하는 방법이 있는데 그건 이제 우리가 안 배워요.
그러니까 초기 값을 인터체인지 한 걸로 초기 값 생각이 나오는.
네. 그러니까 쭉 로우 리덕션을 하면서 인터체인지가 있으면은 LU는 못 한다고 봐야 돼요.
그리고 9.4 챕터를
네.
원래 하나.
예, 그건 스킵해요 우리. 네.
무조건 늦게 왔어요.
네.
감사합니다.
네.
그 LU 쓰면은 해 가는 게 편해진다고 하셨잖아요. 근데 그러면 이제 계산을 총 2번.
그거네요.
근데 그러면 그럴 바에
그냥 한 번에.
A를 한 번에 해서 한 거죠.
네. 그러니까 그게 우리가 정확하게 증명은 하진 않는데요. 이렇게 2번에 나눠서 그러니까 굳이 이걸 2번을 해서 하고 또 LU까지 우리는 또 구해야 돼요. 그리고 LU를 구하는 것 자체가 에슐론 폼을 만드는 과정이거든요. 다만 이제 우리가 솔루션을 구할 때는 이걸 리듀스드 에슐론 폼까지 가요. 근데 리듀스드 에슐론 폼까지 가지 않고 이제 에슐론 폼에서 멈추고 거기서 LU를 얻은 다음에 그 다음에 또 2번의 스텝을 거쳐서 푸는 거예요. 아까처럼 트라이앵글러를 2번 해서. 근데 이게 전체적으로 굉장히 더 그러니까 더 복잡해 보일 수 있는데, 이게 그러니까 B들이 이렇게 저렇게 계속 바뀔 때 이걸 LU를 한번 만들어 놓으면 매번 로우 리덕션을 다시 해서 이거를 뭐 할 필요가 없이 바로바로 좀 할 수가 있다는 좀 재활용의 측면이 좀 있어요.
근데 한 번 할 때는 딱 큰 장점은 없는데 계속 B가 바뀔 때
그렇다고 볼 수 있어요.
슬라이드
네.
8번이요.
네. 학생님 떠들지 마세요.
그게 아니고 제 친구가 계속 물어보는데.
그래도. 네.
죄송합니다.
네. 주세요. 네. 슬라이드 8번.
그러니까 이거는
네.
U를 바탕해가지고 L을 푸는 거잖아요.
네.
그러니까 이거는 좀 다르죠. 이거는 L로 바탕을 U를 찾는 건가요?
그러니까 이제 LUX 이꼴 B가 있어요.
네.
근데 이게 이렇게 생긴 트라이앵글러고 이건 이렇게
네.
생긴 트라이앵글러예요. 그 다음에 이건 이렇게 생겼고 이건 이렇게 생겼고요. 그러면 이 전체 덩어리를 Y로 보면 이거는 이제 요거 작은 삼각형 곱하기 어떤 Y, 그 다음엔 요게 나와요. 그럼 먼저 Y를 먼저 이거를 통해서 푸는 거예요.
네.
그 다음에 요 안으로 들어가 보면 이제는 UX 이꼴 Y가 되고 U는 그러면 어퍼 트라이앵글러가 되고요. 그 다음에 X가 되고 그 다음에 이 Y가 우리가 구한 요 Y가 돼요.
네.
그래서 요거를 중간 값을 구했으면 그거를 다시 요 어퍼 트라이앵글러 요거를 가지고 실제 우리가 구해야 되는 요 X를 푸는 거예요.
아, 그게 바로
네. 요 우리는 요 안쪽까지 요 X를 구해야 되는데 이거를 일단 중간 단계로서의 Y로 놓고 그렇게 푸는 거예요.
이거 좀 헷갈렸어요. 이거 다루기 위해
네.
여기 앞에 U가 있고 저는 L이 있으니까.
네.
감사합니다.
네, 그래요.